Well, greetings everybody. So here's a problem from our assignment on my math lab that I think is very important to spend some time on. So this video may be longer than you want it to be, but if you're just looking for the short answer to this, I'll run through a summary of what I'm going to say before I go into depth about it. Okay? Now, I'll let you read this situation here if you want to. I'm not going to read it to you. I'm going to go straight to my understanding of how that information is given. Okay, so if you want to pause it and read it and see how that matches up with what I say, you can go ahead and do that. But here's how I understand it. Here's how I would think about it. The scenario is that we have an object attached to a spring that's fixed to some point vertically above it. Okay, and what we want to do is, suppose this is at rest and it's not moving. We could compress the spring or stretch it and then let go, and then the object's going to move up and down, okay? Eventually coming to a stop. What I want to do in this problem with you is think about how we would track the up and down motion of this object, okay? Now, in order to do that, we'll have to define some variables and understand some constants and impose a coordinate system on the situation. But we can do that. That's something that scientists and engineers do a lot. We might look at a situation, impose some measurements on it so that we can quantify it with equations and so on. Okay, so we'll say that with this vertical axis imposed on the situation, it measures the position of the mass at time t. It's at this rest position, which we mark 0 when it's you're not touching it. Okay, it's still nothing's acted on it. It's not moving. It's just sitting there. Okay, we'll compress it. We'll compress the spring to position y naught or y subscript 0, and then let it go, and then it will oscillate like I was saying. Okay, as far as how this coordinate system is arranged, the positive y values will be above 0 where the rest position is, and the negative y values will be below it. You might think that's obvious, but we could do it the other way. We could put the negatives up and the positives down. Okay, it's just a matter of convention how somebody does it. But we'll compress to this point, let it go, and it's going to bounce up and down, and we want to describe how it moves with some functions and their derivatives. Now, I think this is an important problem to spend some time on because it's from something called simple harmonic motion, which is the mass spring problem that you see here. But it's everywhere, like in mechanical systems of all kinds. If there's a vibration, then it might be that there's simple harmonic motion as the explanation for it. So I think that this is important. And it's not just in physical systems, like say in mechanics that mechanical engineers deal with. In electrical systems, there's an analogy to this that happens too, with circuits that have capacitors and inductors in them. Radio tuners work this way, and so on. We might not see bouncing up and down like a mass on a spring, but something like that is happening in the circuit. So it's an important idea. That's all I'm trying to say. So quick summary. We're given this function where y measures the position on this axis in meters at any time t in seconds. That's what this does. There are some constants. We want to find this derivative, okay? And we use the chain rule to find the derivative. We simplify it to this, okay? We determine that that's a sine wave, where we can know a little bit about the graph by way of this being the amplitude and this number determining the period. All right. If you want to graph it because that helps you think about it, you can do that. I have a kind of a in-depth analysis of what the graph looks like there. And then to answer the questions, one of the questions is, suppose the mass was 16 times as big, how would that affect the amplitude and the period of the derivative? And so I just take what the amplitude and the period were, and I put a mass in 16 times more than that, simplify it, and I see that it's 1/4 as big in one case, 4 times as great in another. Okay, so that's the quick summary of the problem. If you're happy with that, go for it and work the problem, okay? If you want some more detail, here's what I would say. So yes, I'm given this function, which measures the position of the object at any time t on this axis. Positions in meters, times in seconds. Okay, there are some constants. Y naught is this initial position of displacement. We compress the spring to this position Y naught, we let it go, and then it oscillates. K is the spring constant. Some springs are stiffer than others, okay? So how much this moves would probably depend on something about the spring. How stiff the spring is, or so on, how elastic the spring is. So K is a number that quantifies that. It's a constant though. And M is the mass of the object. So those are constants, right? In calculus, I've made other videos where I said it's important to be aware of when we see a function, what in that function is a constant and what's a variable. Y and T are the variables. Y naught, K, and M are the constants. So when we apply the rules of calculus, we treat constants like constants and variables like variables, okay? So, all right, that's what we're given. Oh, I forgot one more thing. I know in reality, any real mass attached to a spring, although you could displace it, let it go, and it will oscillate, will eventually come to a rest. There's dampening forces that make that the case. In this problem, for simplicity, it's assumed that we'll ignore the dampening forces and it will just go on. Okay. All right. The dampening forces incorporated into this will make it more complicated. It's not something that we can deal with right now. So we'll just use this. All right. So here's the first part of the question is it says, what is this derivative dy over dt? Okay. Which is just the derivative of this function right here. Y naught cosine t root k over m. Okay. But I'll say something. Remember, I already did a quick summary. I was going to go into more detail. I think the detail is important. I really think that if you're going to do a science or engineering field that's very heavy in math, you'll have to be as good at math as I am. All right. I went to electrical engineering school, so I know what it's like to go through that. So I'm going to tell you a lot of stuff. And even if it doesn't all sink in now, it will be, I hope, on your radar as something to think about as we go on. All right. So I'm looking for this derivative. This derivative will tell me the velocity of the mass at any time. So this function tells me the position of the mass at any time, position on this axis. And if I take the derivative of that, I get the velocity of the mass at any time. If its position changes, it's moving. And if it's moving, it has a velocity. That derivative tells me that. Now, one thing that I haven't said so much in the videos I made recently is the derivative is called the instantaneous rate of change. I'm just curious, like I think words are important. Why do you think that word is instantaneous with the word instantaneous having this other word in it, instant? Okay, it tells me the velocity of the mass at any moment in time, at any instant in time. Okay. It's a little bit of a paradox because at any moment in time, at any instant in time, everything's standing still. Nothing's moving. At 2 o'clock today, everything was standing still. Nothing was moving. Maybe there's some movement from 2 o'clock to 2:01, as time passes, but at any instant, everything's standing still. So it's a little bit of a paradox that there could be an instantaneous velocity or an instantaneous rate of change, but it's all because this is a limit as delta t goes to 0. All right, so that's a little bit conceptual, but still I want it to be something you think about. So we want the derivative of this. That's our objective. Let's think about this. What rule should we use to find that derivative? The rule that we should use is the chain rule. One form of the chain rule is this. The derivative with respect to x of cosine u is negative sine u times du over dt. Okay. I made a little mistake on that. This should be the derivative with respect to t. Okay. Because that function u is a function of t. All right. The variable in that function is what? Is it k? Is it m? Is it x? No, it's t. Okay. So we'll do the derivative with respect to t, d over dt of cosine u is negative sine u times du over dt. Okay. All right. That's the rule that would be applicable to find the derivative of this function. Remember, k and m are constants, and root k over m is a constant by extension. All right. If 18 is a constant and 2 is a constant, then the square root of 18 divided by 2 is 3, and that's a constant. All right. Okay. So here goes. There's my function. I copied it down. Here's our rule. Since y naught's a constant, I carry that down. The rules of calculus allow for that. If that's a constant, it is. That's my coefficient. I bring it down. I get negative sine u, so this is my u, times the derivative of that inside part. What's the derivative with respect to t, considering that t is the variable and k and m are constants? What's the derivative of t times root k over m? It's root k over m. Okay, so there it is. That's the chain rule as it plays out in this example. I will collect some of the coefficients together. I get root k over m times -1 times y naught. That becomes my coefficient sine of t root k over m. Okay, so does this have units? Well, everything's going to have units that we deal with here. Like what we started with. T, that's a variable. What are the units? Seconds. And y, what are the units there? Meters, okay? Position and time. So this derivative will have units of meters per second, or distance over time. Okay, don't overlook the units. Doing the sciences or engineering, it deals with measurement. Measurements are the units. We have to keep track of them as we do our work. How do I know that this is the units, though? I think that's maybe a more important question. The fact that the units are meters per second is one thing. How do I know? Well, I know that the derivative has this comparison with the average rate of change. The instantaneous rate of change is a lot like the average rate of change, so long as that change in the independent variable down there is small. And so what would the units of the average rate of change be? Delta y over delta t. Delta y is change in position. Delta t is change in time. If time passes and something changes position, it moves, right? Okay, so it's got a speed or a velocity in meters per second. Yeah, we were measuring position and therefore change in position in meters, and time and therefore change in time, or a period of elapsed time in seconds. So because these are analogous to each other, the derivative has the same units as the average rate of change, has the same units as delta y over delta t. Okay, and maybe you could think, well, that's why Leibniz notation looks a lot like our notation for average rates of change. Okay, so I have my derivative. There it is. Remember I said the video may be long. I've already done the quick summary. I'm telling you more than you might want to know but need to know, I think. So there it is. Okay, I noticed that they put the units as units per second. All right, in this problem, for some reason, they didn't reveal till reading later on that the units on the vertical axis, the position units, were meters. Okay, so all right, fine. Units per second, distance units per second. If you tell me it's meters, meters per second. Okay, now the rest of the question deals with a little bit of analysis of this. Okay, this is my velocity at any moment in time. Remember, that's what this tells me. As this object moves up and down, it has a velocity. It's possible to say it's moving this fast at any moment in time. That's what this does. You put a time in, you do the math, it tells you how fast the object is moving as it oscillates on the spring in meters per second. Okay, but I mean, what does that look like? I mean, as I've seen objects under the influence of vibrations like that, they kind of like speed up and slow down. You know, as the object like goes up, as high as it's going to go, it kind of slows down as it gets up there. It comes to a stop, it turns around, it changes direction, right? And it speeds up as it goes the other way, and then it slows back down when it gets to the bottom. And so that's what we're looking at, right? Kind of speeding up and slowing down, turning around, speeding up, slowing down. Why do I look at it like that? Okay, to do this, I mean, I guess to really understand it, we would have to know how to graph a sine wave. So when you take pre-calculus or trigonometry, you learn how to graph sine and cosine waves. Or even if you had a graphing calculator, you should learn how to understand how all these numbers influence what that sine wave looks like. Because why is that important? Natural vibrations can be explained by sine and cosine waves, as you see here. So this negative means I have a sine wave that's reflected across the x-axis. This coefficient, y naught root k over m, is the amplitude of the sine wave, meaning its maximum and minimum values on the vertical axis. Okay. This constant here, this coefficient of the variable, influence what's the period. Okay. Every sine wave has a natural period after which it just completes itself again and again and again. Normally on a sine wave, that period is 2 pi for it to complete one up and down oscillation. And after 2 pi, it repeats itself. And after another 2 pi, it repeats itself. That's what the normal period of a sine wave is. If you have a number here multiplying the variable, the period becomes 2 pi, which is the ordinary period of a sine wave, divide by that number. Okay? So this reflects it, turns the sine wave upside down across the horizontal axis, or the x-axis, or the time axis in this case. This number makes the amplitude different. The wave will go up to a maximum point of y naught root k over m and down to a minimum of negative y naught k over m on the vertical axis. And then the period is different too because of that number. It's now 2 pi over root k over m, whatever that is. So I graphed it. Okay, we got velocity on the vertical axis because that's what this tells you. Time on the horizontal axis. Velocity in meters per second, time in seconds. So here's a sine wave, which is reflected from what it would normally be, going down to a minimum and maximum, up to a maximum of y naught root k over m, having a period or a horizontal distance to complete one cycle of 2 pi over root k over m. And then I've done an even deeper analysis, like here the velocity is negative. That means it's moving downward. But notice it's getting more negative, so it's speeding up in that direction. Then it gets to some maximum speed in that direction. And then in this phase right here in 2, I notice they're negative numbers, but they're becoming smaller negative numbers. So it's still moving downward, but it's slowing down. Remember, it's going to go down, but it's going to start slowing down as it gets as far as it's going to go. Then it'll stop and turn around. Turns around right there when the velocity is 0. So in order to go down but transition to going back up, it has to come to a stop at an instant. All right, so that's what that is. And then it starts going up faster and faster, reaches a max speed in the upward direction, slows down, turns around again. All right, that's what all this is. Okay, so that's a fairly detailed analysis of this sine wave, which is our derivative and velocity of this object oscillating on a spring. I hope that you remember that, or at least some of this from pre-calculus, or at least have it start to come back to you as I mention it. If not, you can always ask. I'll clarify whatever you need. Now, the next questions are, like I said in my summary at the beginning of the video. Well, so it says like this. Okay, so you got this mass on a spring. You got this object on a spring, and it goes up and down. It does appear that what the amplitude and period are of this wave that describes the velocity would be different if the mass or spring constant, m or k, were different, or if the this original displacement, y naught, was different. So if any of those things were different, we might get a wave with a longer period, meaning more time to complete one up and down motion, with a higher maximum speed, meaning a larger amplitude, or whatever. It would change that, all that stuff, right? Why is that? Well, because all that stuff, y naught, k, and m, is all part of this formula. If you change any one of those, it's going to be different. You're going to get different numbers. So the question is this: how would the velocity be affected if the experiment were repeated with a mass 16 times as great? So instead of a mass of m, we're going to have a mass of 16m. And it just says, well, how would the amplitude and velocity be different? All right. So I've explained out of this how the amplitude and the, oh, sorry, I read that wrong. How the amplitude of the velocity and the period will be different. So I've already explained what those were in this. And here we go. The old amplitude was y naught root k over m. If you make m 16 times as big, it will be 16m. I can factor out this root 16 times y naught root k over m, but 1 over root 16 is 1/4. So that says the old amplitude times 1/4 is going to be the new one. All right, the new one is 1/4 of the old one. All right, so now I got my statement. If that mass is 16 times as big, that would reduce the amplitude. The new amplitude will be 1/4 of the original. Okay, I guess I can see that if I put a heavier mass on there, that it might not oscillate quite as far in either direction. All right, that's what it says. Okay. Uh, what about the period? How's that going to affect the period? Well, here's the old period. The new period would be this, but with 16m in place of the mass. So instead of m, I get 16m. I do the same sort of thing. I can factor out root 16 there. The rules of algebra allow for that. That's like dividing by 1 over 4. So dividing by 1 over 4 is like multiplying by 4. So this turns out to say 4 times the old period. So the new period equals 4 times the old period. Okay. What would that mean? I said the period is the time it takes to complete one up and down cycle, get back to where you started. Well, it's going to take 4 times as long to do that. Okay, because the new period is 4 times whatever the old one is. That's literally what that says. Here's the old one, there's 4. Okay, so then we see here the period of the velocity will be 4 times as longer. As far as like time goes, it's going to take 4 times as long to go up and down and back to where it started. One cycle of up and down. Okay, so we got it. All right, I warned you. I said it could be a long video because I think there's a lot to say about this. Way more to say than I have here, and I think, likely, most of you, if you're in calculus, this is something that you'll spend a lot more time on when you take additional calculus classes, physics courses, and beyond.